Hi there. Welcome back to the wild world of sediments and sedimentary rocks. This is part 5, so you should have already gone through parts 1, 2, 3, and 4. In part 5, we're going to illustrate the process all the way from erosion to deposition. But we're going to use one example, the fluvial example. In other words, river and stream flow. So I told you earlier, I have been blessed with having been able to visit more than 50 countries uh, in 4 continents. So I've seen some of the major rivers in the world. I wanted to show you some examples of these. Clockwise from the top left, you can see the Tiber River in the city of Rome, Italy. Next to that, you have the Volga River in the city of St. Petersburg in Russia. Next to that, you have the famous Danube River uh, near the city of Prague in the Czech Republic. And on the bottom, you see the Douro River in the city of Porto, Portugal. By the way, that's where they make the good port wine. You know, rivers and streams are very powerful agents of erosion. Uh, a river or a stream may be defined as water that flows within a channel. The gradient of the stream is the vertical drop in a given horizontal distance. The velocity of a stream is defined by the distance traveled by the flowing water per unit time. Now, what factors affect stream velocity? Well, the gradient. The steeper the gradient, the faster the velocity. Channel size. Water flows faster in a narrow channel than in a wide channel. Also, the channel shape. Uh, the roughness of the channel's bed and banks affects the velocity and increases overall turbulence. The picture that you see is a beautiful area in upstate New York called Oswald Chasm. You should know that the velocity of flow in a river or stream can be approximated using Manning's equation, where velocity is a function of a constant, 1.49, multiplied times the hydraulic radius times the gradient divided by the Manning roughness coefficient. The hydraulic radius is the cross-sectional area of the stream divided by its wetted perimeter. The gradient is the vertical drop in a given horizontal distance, and the Manning roughness coefficient will vary anywhere between 0.012 to 0.05. The highest values occur in mountain streams with rocky beds, and the lowest value occurs in a channel that is lined with smooth concrete. Typically, streams and rivers tend to meander and deposit what we call point bars. Well, meanders are bends in the river as the river or stream, as it flows, seeks a path of least resistance. Now, the outside of the river channel is what we call the erosional side. Why? Because water flows faster in this area due to centrifugal force. Conversely, the inside of the river meander is the depositional side because water is flowing at a slower velocity. So deposition typically takes place on the inside of that meander. Point bars are sandbars or gravel bars that are located along the inside of stream meanders. In the picture, you can see a classic point bar on the inside of a meander in a river in Texas. Now, the erosion in streams takes place via several processes. One is what we call hydraulic action, or the pressure that is exerted by the flowing and rushing water to dislodge rock fragments. Also, you can have the process of abrasion or erosion through impact and friction. Through solution, due to the ability of water to dissolve certain rock types, like we talked about in chemical weathering. And also through the down-cutting power of the stream and the power of the stream to also cut laterally to widen its channel. The picture is out of the Paluxy River in Glen Rose in Texas. So what are the mechanisms of sediment transport in stream? Well, you have translation, saltation, suspension, and solution. In translation, particles move by sliding or rolling along the stream bed. Larger grain particles tend to move this way. Saltation implies jumping. A particle may be picked up, rise, and then drop again. Typical sand-sized particles tend to move in this fashion. Suspension implies floating. Some particles are light enough, like clay particles, to simply float down the stream. And solution are particles or mineral matter that may be dissolved by the water until it reaches some point like the ocean where it precipitates into solid mineral matter again. The outcrop that you see here is basically a sandstone outcrop in the Garden of the Gods in Colorado. I'm trying to topple down this big bluff or this big block. Guess what? I did not succeed. Now, deposition in streams occurs when the stream or the river will lay down the sediment load that they carry. Deposition is affected by a decrease in the velocity of the stream, a decrease in the gradient, or a decrease in discharge. Where would you expect deposition to take place in the fluvial system? Well, we already talked about the meandering streams, where sediments are generally deposited along the inside of the meander, the point bars that we talked about. Also, we can have a braided stream system that will form in areas of low gradient and high capacity. Along floodplains next to the streams channel, sediment may accumulate, forming what we call a natural levee. And deposition generally occurs when the stream gradient abruptly decreases, as found in deltas and in alluvial fans. The picture is a stream in the Black Hills of South Dakota in the U.S. Now, this is an interesting diagram because it basically relates erosion, transportation, and deposition as functions of the water velocity and particle size. Velocity is plotted on the y-axis and particle size along the x-axis. Notice that you have two curves, a solid curve. Above that curve you have erosion, then you have a dash curve, and below that curve you have deposition. In between you have transportation. Now, a 0.001 millimeter particle would erode at a flow velocity of 5 meters per second or greater. That is shown in yellow on the diagram. As particle size gets larger, the minimum flow velocity needed to erode the particle decreases. That is shown by the blue arrow. Now, that's up to a point. The lowest flow velocity, for example, to erode a 0.5 millimeter particle is about 0.3 meters per second, as shown in red. To erode particles larger than 0.5 millimeters, the minimum flow velocity rises once more. That's shown by the orange arrow. As far as deposition is concerned, a 0.01 millimeter particle would be deposited with a flow velocity of 0.001 meter per second or less. That's shown in green in the diagram. And as the flow velocity increases, only larger particles will be deposited. That is shown by the purple arrows. So again, above the solid curve, you have erosion. Below the dashed curve, you have deposition. In between, you have transportation. Now, river floods are a significant natural disaster. So we should talk about floods and particle size. Let me define three terms for you at this time. Stream discharge is defined as the volume of water passing a given point per unit time. Discharge is a function of the velocity times the width times the depth of the channel. The competence of a stream is defined as the maximum size particle that a stream can carry. The capacity of a stream is defined as the total volume of sediment that a stream can carry. All of these factors can increase dramatically during floods. The picture, you see the Lavon Lake Dam releasing water after flood conditions in the U.S., in Texas. Here I want to illustrate for you the example of how both competence and capacity increase during floods. By the way, the picture that you see here is debris that has accumulated after a flood in Texas in 2015. The river actually rose more than 30 feet, even above the interstate highway that you see here. Now let me give you this example. In a given flood, competence will increase as the sixth power of the velocity. So take this example. Say that during normal conditions, a stream has a competence of 3 millimeters. That means that it moves a particle that is 3 millimeters in diameter. That would be a small pebble, right? But during a flood, say that the velocity increases by a factor of 2.5. So the competence will increase to the sixth power of 2.5. So that's 2.5 elevated to the sixth power, and that's equal to 244. Now the original competence was 3 millimeters. The new competence is 244 times larger than the original. So the new competence is 3 times 244, which is 732 millimeters. The bottom line, a stream that normally has the competence to carry a small pebble now can move boulders. In floods, the capacity also increases as the discharge square or the discharge cube. So if the discharge, for example, is tripled during a flood, the capacity will increase somewhere between 9 to 27 times greater than normal. Pretty significant, huh? I conclude now by showing you some pictures of some flooded areas that occurred in 2015. These pictures are mainly in Plano and Wiley in North Texas. Well, we have completed part 5. We have 2 parts remaining, part 6 and part 7. So see you in part 6.